Hi, welcome to the second class of quantum physics. That is quantum physics made easy. In this class, we will be pinpointing two things, that is wave functions, eigenfunctions, eigenvalues, along with the eigenvector. And dealing with a university type question, state the admissibility condition of wave function. Before going further, we have to explain what you mean by commute or commutative principle. If AB is equal to BA, we can say that they commute each other. Similarly, we should be careful while dealing with the quantum mechanical operators. The quantum mechanical operators, momentum operator, position operator, Hamiltonian operator, Laplacian operator, etc. you might have heard. While dealing with such operators, operators are different from usual algebraic quantities. How? Operators do not necessarily commute. That means some operators, when selecting a particular combination, may commute, but others will not commute. For example, if you are doing the operations of momentum followed by position, momentum operator is px cap followed by x cap. That is position operator and momentum operator are doing. We have to first perform the momentum operator, then the position operator. If you are reversing it, it will not be equal on a wave function. A very simple example is wearing the shoe. You are first using stockings, then using the shoe. You just imagine that you are doing the reverse thing. First you are wearing the shoe and then using the stockings. Is it in proper way? No, they are entirely different things. Similarly, here when an operator momentum is followed by s cap, it will not be equal in the other way around. But there are instances where such operations will commute. For example, kinetic energy operator T cap, Tx cap is followed by potential energy operator on a wave function will be same as the other way. That is first momentum operator, then kinetic energy operator. They will commute. My point is that operators are different from usual algebraic quantities, and we should be careful while dealing with the operators, which will be more clear in the coming classes. Now let us go to our intention in this class. We have to introduce what is a wave function, eigenfunction, eigenvalues and eigenvector. A wave function is denoted as psi. If it is a coordinate system, it will be psi x, y, z appearing in the Schrodinger equation. Schrodinger equation, you know, it is equal to h cap psi is equal to E psi. We have explained in the last class. H cap is equal to this quantity, and when it is substituted, h psi is equal to E psi, we have the form of the equation like this. Now, wave function is a function of psi appearing in the Schrodinger equation, h psi is equal to E psi in the wave mechanics. So, what is wave function? It's a mathematical expression. It's a mathematical expression, function or quantity used in quantum mechanics to describe the wave, energy level, eigenvalue, location in space, the coordinate system x, y, z of any moving particle as an electron in an atom. Meanwhile, we want to use wave functions in all equations and in the quantum physics. Therefore, some more things you should understand. Wave function itself is not having a physical significance, but the square of the wave function or the modulus psi square is having special meaning. That is giving the probability of finding the particle in a confined area. For example, the physical significance of wave function psi is that the square of the absolute value, that is a modulus of psi square at a point, is proportional to the probability of finding the particle in a small volume element. Small volume element can be denoted as dx, dy, dz. It is denoted also as d tau. D tau means dx, dy, dz. At that point, I will repeat, the physical significance of wave function psi xyz is that the square of its absolute value, that is absolute value is modulus of psi whole square. Modulus psi square at a point is proportional to the probability of finding the particle in a small volume element d tau, that is dx, dy, dz at that point. So everybody know what is an orbital, etc. And that concept is developed from this. For an electron in an atom, modulus of psi square give rise to the idea of atomic and molecular orbitals. So what do you know? You know that an orbital is a region in which an electron may be found in an atom or molecule. So that is regarding wave function. Next is the eigenfunction. Almost a similar meaning here. Depending on the boundary conditions of the Schrödinger equation. At boundary, it should be continuous across a boundary. So depending on the boundary condition, the Schrödinger equation H psi is equal to E psi can be solved for a particle in a system. Then the solution is a set of allowed wave functions called eigenfunctions. So we are depending on the boundary conditions, Schrödinger equation H psi is equal to E psi is solved for a particular particle. For example, for an electron in an orbital. Then the solution is a set of allowed wave functions, satisfactory wave functions called eigenfunctions. Or the allowed wave functions of quantum mechanics is called eigenfunction. That is more simple. The allowed wave functions, all wave functions are not allowed only when it is satisfying conditions, the boundary condition will be allowed or acceptable. Such a wave function in quantum mechanics is called eigenfunction. The allowed or satisfying wave function of quantum mechanics is called acceptable wave function in quantum mechanics is called eigenfunction. Next is eigenvalue, called eigenvalue also. Eigenvalue. What is an eigenvalue? Each of the eigenfunction corresponds to an allowed energy level. Each of the wave function or eigenfunction corresponds to allowed energy level called or acceptable energy level called eigenvalue. So what is eigenvalue? Eigenvalue is the possible value derived from a differential or integral equation having solution that satisfy certain special conditions. We will see what are the special conditions soon. So eigenvalues are the possible value derived from differential or integral equation having solution that satisfy certain special conditions. And the fourth one is an idea regarding eigenvector. Eigenvector is a non-zero vector. It is not equal to 0. When applied, does not change the direction also. That is called eigenvector. So before proceeding further, just to recall, we have h cap is equal to minus h cross square by 2m del square plus v potential energy of RT. The first term is called kinetic energy. And the Schrödinger equation is this h cap then operating with a psi xyz. That is equal to E equal to psi xyz. From here, we can say that this E value is called eigenvalue. And eigenfunction and wave functions are denoted as psi xyz here. And here is an operator inside it. So that is called a Hamiltonian operator. In general, Schrodinger equation h cap psi is equal to E psi, in which we are applying the Hamiltonian operator to systems described by psi with respect to the coordinate and time. For that, we have to first answer a university type of question. That university question is, what are list the any two or any three or any one admissibility condition of a wave function. In what circumstances we can accept the wave function? For time being, let us simply assume that wave function is, for a stretched string, it is equal to the amplitude. If for a stretched string, if it is vibrating, the wave function psi can be denoted as amplitude. In what all conditions the admissibility condition of wave function in equations are there for Schrodinger equation? Wave function psi will be acceptable. Let us see the three very important conditions in which the wave function can be acceptable. So wave function psi will be acceptable only when it is satisfy or fulfill or achieve or attain the following requirements. What are they? The first one is psi must be finite everywhere. It should have a clear, significant value. It should have finite or zero value. It should be there or not be there. It should have a particular value or no value at any point. Why? Suppose I is infinite, it is having any number of values. What happens? Then the probability psi modulus square is called the probability. I have told you. The probability of finding anything in a confined region. The probability of finding the particle will be infinite. So what is that? If it is infinite, that will violate uncertainty principle. So this statement that it is not finite becomes against uncertainty principle. Therefore, psi should be finite. It should have a definite value. Psi should be finite, then only it will satisfy the uncertainty principle as well. And if it is having any number of value, then the probability of finding the particle will also be infinite and will violate uncertainty principle. So first point, remember, psi must be finite everywhere. Second point is, psi must be single valued. Only one value for that. What's the meaning? If it is not single valued, what happens? Or suppose psi has more than one value at a given point, coordinate system, then what happens? Then there will be more than one value of probability of finding that particle at that point which is not acceptable. In that case, psi will be the probability of finding the particle at that point will have more values. So psi should be single valued. Single value. You can see that 1 and 2 are almost having same sense and meaning. So psi must be single valued means it should have a particular definite value only. If it is having more values, more number of values, the probability also will be different for different values. And for that case, psi should be single valued. The most important and the third important condition is psi should be continuous and first derivative everywhere. That means it should satisfy the boundary condition. What is it? In the Schrodinger equation, there is a term partial differential square psi by ds square in the del square along the x-axis. Del square is a Laplacian operator. Along the x direction is a partial differential of square of psi divided by partial differential square. Dou square psi by dou x square must be finite everywhere. Then only we can locate and understand the energy, position and all factors of the particle, which is possible only when dou psi by dou x, the first differential, the first derivative, second derivative will be finite only when the first derivative d psi by dx has no discontinuity at any boundary where the potential changes. This is possible only when the first derivative dou psi by dou x is continuous, or it is not having a discontinuity at any boundary where the potential changes. So since dou psi by dou x is continuous, what you can say? Dou psi by dou x will be continuous only when psi also is continuous across the boundary. Psi also is continuous, then only it will be continuous. And it satisfies the boundary condition. It satisfies the boundary condition, that is psi is continuous across the boundary. So what you can say, think in the other way around, psi is continuous. Then the first derivative dou psi by dou x will be continuous. And in that case, dou square psi and dou x divided by dou x square, that is the second derivative must be finite everywhere. So these are the admissibility conditions of wave function. I will repeat. Admissibility condition, first one is psi must be finite everywhere. Then second one, psi must be single valued. And third one, psi should be continuous and first derivative everywhere and satisfy the boundary condition. With this, we'll stop today's class. We'll come next class with the concept, a more developed concept of quantum physics. Bye.